What's up, Calc C, Calc BC people? We're in Riemann sums, area underneath a curve, 4.3. Okay. What we are going to do is find the area underneath the curve using a Riemann sum. What the definition is, and so on. Basically, we're starting integration. We already have done a little bit of integration already with trig and stuff like that in the last section. We're going to get more into what integration actually means, starting kind of now and working our way forward. So we want to understand the definition. We want to use Riemann sums to find the area underneath a curve. So a couple questions is, how do you find the area underneath a curve? Well, if it's a piecewise graph, meaning there's basically a piece here, a piece there, kind of there's pieces all around. If it's linear or circular, I can find it using like area formulas, right? Like base times height, or pi r squared, divide by however many things there are. So I can very easily, if I wanted to, find the area of this function, this piecewise function here. I can say, okay, well, that's 1 times 2 divided by 2 is just 1, so that's just 1. This is 2 times 2 is 4. This is now a trapezoid, so I can do base 1, which is 1, plus base 2, which is 2, so that's 3, times 1, which is the height, divided by 2, so that's just 1.5. This one is 1 times 1 is 1. And then this is pi r squared. This is pi r squared, but it's over divided by 4, right? And radius is 1, so that's just going to be pi over 4. And then I would just add all those pieces up to find out the area of that piecewise function. It makes it easier that way when it's really nice in geometric shapes. But what happens if it is not a nice geometric shape? What happens if the graph is curved, where it's not a circle or a square or something like that? So we have a couple different things. The most common way is to use what we call rectangles. Not what we call, it's a geometric shape, duh. It's used by like the Greeks and everybody else. We have a couple different ways we can do this. So this is an increasing function, right? It's going up. So that we can use a left Riemann sum, which means the height of each triangle comes from the left side. So if I want to find, scared me, that was my daughter's like Finding Nemo like playset or something. That was kind of scary, just making noise, and he's not even over here. Oof. My heart's like beating a mile a minute right now. So I want to find an area from here to here. Okay, I'm going to go from here to start. I'm going to make sure I have the amount of rectangles I need. It'll tell me how many rectangles I need, and I want to make the space even. Okay, and so I go from here to here. This is the graph. And then I go over to find my next rectangle, and then I'm basically, so there's one rectangle, then I'm going to go up there and so on, basically all the way up, and then make my rectangles from there, right? Find the area of each, boom, 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 and then that's your left-hand Riemann sum. This is what we call an under approximate, right? Under approximate. So a Riemann sum is just an approximate value. When we do left hand or right hand, it's never going to be the exact, because what's going on is our rectangles are this wide, right? And because they're this wide, or however wide they are, it can't get a good grasp of the actual full area underneath the curve, because in the left hand side we have this little piece here, this little piece here, and so on all the way through. In the right hand side, we're coming from the right, so I'm working my way back this way. I'm going to the function, then going over. So this is an over approximate, okay? Over approximation here, because I'm above the graph, and therefore this answer is going to be above. Like, these are going to be little spaces above my function, and therefore the area is going to be over an estimate. So I can never get an exact value if I use rectangles, a finite many rectangles. So if I have a finite number, hopefully you know what that means. Finite means like a number we can count, right? If I have a finite number of rectangles, I can never get the exact answer, all right? So how do we get better and better estimates? We just talked about these, okay? So we just talked about those. If I want to get better and better estimates, I'm always going to have rectangles, but I'm going to use more of them, and I'm going to make them narrower, all right? So I don't want a rectangle, like these are okay. This is a better representation of what's going on. But you can see that I still have some space below and then a lot of space above, right? And that doesn't really come in handy too well. If we look at this one, my rectangles are narrower and narrower and narrower, and this is actually a left hand, or this is a right hand. This is a right hand, and this is a left hand, okay? Riemann sum. And you can definitely see that from the right side, it looks even closer because there's not much stuff above it, but there are some areas that are still below it. And the more and more and more and more rectangles we get means the skinnier the rectangles get in terms of height, okay? Because our height is from here to here or from here to here, right? Those are our height values, these are not our height values, okay? That's not our height. And so the more rectangles we make, and the skinnier they are, the more we can kind of compact them and compact them and compact them, and we can get that curve. All right, and we can definitely get that curve. So I'm having trouble here. Okay, here we go. So the area of each rectangle is the base times the height. Okay, but now we got to think about this. So the height is really the delta x, the change in x. Okay, from one to the other. F of x is just like the length of each. So if I think about each rectangle and I split it down, okay, delta x is that height between the rectangles, and therefore the f of x is just our length of that rectangle. Okay, so again, area of a rectangle is f of x times delta x. Delta x is that change. Ultimately, we want that delta x to be as skinny and skinny as skinny as skinny as skinny as skinny as possible. And so what's going on right now is if I have n rectangles, so if I have n of these, n is just some number, all right, I'm going to say f of x1, which is the first rectangle, times delta x, because we're saying every rectangle has the same width, right, or the same height. And so f of x1 times delta x, and so on, so on, so on. I can do that all the way until I get to f of x sub n minus 1 times delta x, and then f of x sub n times delta x. So this is the end. This is the last rectangle that's being made. Again, it's n. There can be an infinite amount. There could be 100. There could be a million. Whatever it is. Okay. And so you haven't really seen this notation before, but this is called a summation. So I'm summing f of x1, f of xi times delta x. So xi, this is just how I write it. I is from 1 to n. Okay, from 1 right here, right there, right there, okay, to n. So I'm starting at 1, going to n. That's where those numbers come from. F of xi, so it's xi because there's an infinite amount of x's. All right, and then delta x is because it's the same width or the same height of each rectangle. That's why it stays there and stays the same. All right. Now, what we ultimately want to do is, like I said before, we want the height of each rectangle, the delta x, to be as close to 0 as possible. And so we want to make those rectangles as small as possible. And because we can do that, that gives us the area of the curve. And therefore, what we're doing is we're taking the limit as n approaches infinity. So once n gets as big as possible, I think I'm in whatever direction, I don't even know, because it's inverted or whatever. I'm going this way, but if n is going as big and big and big and big and big as possible, all right, that means our delta x's are going to be as small and small and small and small as possible. All right, so that's just the limit definition of an integral. We didn't really talk about that in AB. We don't really need it in BC, but that's kind of where that integration comes from and kind of why that notation is used. Okay. All right, so I want to use a left-hand Riemann sum and a right-hand Riemann sum to approximate the area underneath this curve from 0 to 1 using 4 intervals. I think this is the only problem I even have on this paper. Oh, I got one more. All right, so what I want to do is, because I have a decreasing function, we know that our left-hand Riemann sum is going to be an over approximate, so this is going to be an over. This is a right-hand Riemann sum, so we know this is going to be an under, because again, it's a decreasing function. Okay, and so I want to go from 0 to 1, but what do I know? I want 4 intervals, so I want to take the space. Basically, what I'm going to do to find that, I'm going to take the b minus a and divide by how many I want. So b is 1, a is 0. Okay, so 1 minus 0, divide by 4, and that gives me the space of each interval. So this we know is going to be 3/4. We know this is going to be a half, and we know this is going to be 1/4. Okay, and I'm going to now use that information to find all this other information. All right, so I'm going to now draw my rectangle. So I'm going to go up here. I'm going to come over to this one here. I'm going to then do what? I'm going to come over from there to this one here, which is right there. I'm going to come over and so on. I'm going to basically follow that. Oh, my lines are not straight, but you can see what I'm doing there. Okay, so this is your left hand right here. Left hand. Your right hand, we have the same thing. Okay, we're going to get a quarter, right? We're going to get a half. Oops. And then we're going to get 3/4. And we're going to now right hand, so this means it's an underestimate. So I'm going to go from here to there. Oops. There. Oh my God, I can't draw. I can't draw a straight line. It's hard. It is hard. I heard Mr. Schaefer, young Schaefer, can draw a mean straight line like he's a boss. And then we got from there to there. If that's what I heard. That's a terrible. I'm sorry. You know what? Hopefully you understand what I'm doing. I'm having a hard time drawing straight lines here. And so what I want to do is I want to find the area between these guys. So let me get rid of some of this here. Oops. Nope. Okay, there we go. Cool beans. And how do I do that? Well, basically I want to find the area of each box, okay, and I want to add them all up. So in this case, the area of this integral of this curve is going to be approximated, okay? That's what those symbols mean. Hopefully we don't use equal signs because it's not actually equal. We're not doing that yet. And so this one here is going to be f of 0 times a quarter. So we'll do it this way. So 1/4 is the width of each times f of 0, okay, plus f of 1/4, okay, plus f of 1/2, plus f of 3/4. All right. Basically, what I'm going to do is I'm going to use a calculator to plug these numbers in. Remember, this is our f, okay, our f of x, our f of our f function, our y equals, and so I'm going to plug that in. A couple different ways we can do that. I'm going to show you one of them using our handy dandy TI-80 something. Okay, so I'm going to go to y equals. I am going to type my function in, which was negative x squared plus 2. So negative xx plus 2. Oops, that's not good. Oh my gosh. Oh my gosh. Okay, negative xx plus 2. All right, and my graph. Hopefully, I don't know what's going on here. I don't know what's going on. 2. Oh, I gotta use a negative. Oh my gosh, this is gonna be a terrible video. I'm sorry, guys. So there's my function. Okay, negative x squared plus 2. And so what I want to do is instead of going to my table and finding those values, what I can do is I can go to second table set. I can go down to make sure my independent is ask. Okay, and then I can go to my second table and I can type in these values. So I'm gonna type in 0, 0.25. 0.5 and then 0.75. Okay, hopefully that rings a bell from last year. That's how you can find those specific values fast. And so I'm just going to add them all up, okay, and then multiply by 1/4, and I get somewhere in the neighborhood of about 1.78125. Remember, I need to go at least 3 places. But if you want to go more than 3, you're more than welcome. You have to go at minimum of 3. You could either truncate or round to 3, but you have to go at least 3. Okay, so that's that one. The next one is going to be fairly similar. I don't want to spend that much time on it because I felt like I wasted a lot of time pulling all this garbage up. But in this case, when I go from the right hand, I'm going to basically take 1/4 because again, that's the width of each, the height of each rectangle. Times, in this case, is going to be f of 1 plus f of 3/4 plus f of 1/2 plus f of 1/4. And if I'm going from the right, I'm never reaching the leftmost point. If I'm going from the left, I'm never reaching the rightmost point. So it kind of makes sense that way, right? And when I do this, multiply everything and do that stuff, I get the area is approximated as 1.53125, and so that's your area underneath that curve. And so you are off by about 25 1/100ths, or about 1/4. You're off by about 0.25, so it's a big difference. All right, when we're talking about small things, like that's a small number, and we're off by that much. That's crazy. Okay, Let's go down to the last one here. Use left and right sums to approximate the area underneath the curve. And so if I'm looking, because my curve is this, I've given it ordered pairs in a table here. Basically what I want to do is, let's do this from now on. Hold on, let's see, left and right. Okay, so I want to find the area from each section to the next, right? So this is going to be different. Not each height of the rectangle is going to be the same value. So because I'm going from the left, I'm saying that the area is going to be equal to f of 0 times the width of the rectangle, which is 2, right? Because 0 to there is 2, plus f of 2 times, then from here to here is 3, plus f of 5 times from here to here is 2, and then plus f of 7 times, and then from here to here is 1, right? So that's kind of what I'm doing there. So that's 4 rectangles that I want to make that one, and that's going to be about 59. So area is going to, there we go, is going to be about 59. Okay, if you do the math, f of 0, right, is 0, so that's just 0. F of 2 is 4, so that's 12. F of 5 is 13, so that's 26. F of 7 is 21 times that, so you'd add those numbers up, and you get 59. Okay, from the right now I'm going to go backwards, so it's going to be f of 8 times and then 1, okay, plus f of 7 times 2, plus f of 5 times 3, plus f of 2 times 2. And then when I do that, I get about 112. Okay, 112. So the area here is equal to about 112. So that's a big difference. This is almost double. All right, so there's definitely a discrepancy there. And if we think about the function's actually increasing. So the function is going up, right? And so a left hand is an underestimate, right? From the left, and from the right it's an overestimate. And so somewhere in the middle would be the answer to that actual value. We don't find it, we don't really care about it right now, but we're just using Riemann sums to approximate areas. Okay? Alright, deuces. That's it for this one. I'll go to the next one. Deuces. Sorry for the terribleness of the video.